Alright guys, thank you for tuning in to another online lesson here for Algebra 2. Um, as we finished up the last target, we actually finished up the last section here that we had for exponential and logarithms. So we are going to go ahead and start a new unit. This unit is all going to be about systems of equations. And today we are going to focus on linear systems and two variables. Um, these notes are basically going to be a complete review of what you did in Algebra 1. We're not really going to present anything new. We're just going to review some topics for systems of equations that we're going to need to be proficient at when we move forward. So let's go ahead and jump into the notes. If you have the option of printing the notes, you can go ahead and print them and follow along in that guided notes packet. If not, go ahead and just take some notes down on a separate sheet of paper. Remember, you guys will be able to use these for your quiz, so make sure you follow along with good notes through the examples. Let's start with the definition for a system of equations. So a system of equation is basically when we combine two or more equations for a given scenario. They have the same variables and we're looking for a common solution. So let's say that, for example, the school is having a play and they have 500 tickets that they need to sell, and there's children's tickets and there's adults tickets. And so they sell all 500. They sell 500 tickets. And let's say the children's tickets cost $3 and the adults tickets cost $5. We can combine the information that we know about children's tickets and adults tickets being our variables to create an equation. When they added together, they're going to be 500. And we could also create an equation to figure out about the revenue. If children's tickets cost 3, we would do 3 times x and add that to 5 times y for adults tickets to figure out the revenue. And so that would create two different equations based on the same variables. And we'd want to figure out how many tickets should we sell of each, essentially, for just an example. So if you look at problem number 1, we see some notation of a system of equations in both 1a and b. In problem 1, we're just verifying that the point is actually a solution to the system. So when we think about graphically, and we're going to do this here in a little bit, but let me just sketch out a visual. Something that we've been doing is we've been finding intersection points on graphs this year when dealing with word problems. And so if we think about two lines graphically, where they intersect, this point would be the solution for that system of equations, one that represents each line. And so what we're doing here in problem 1a is we're just verifying that the point that they gave us is actually the real solution where these two lines intersect. Now, they're not written in linear notation or normal y equals mx plus b, but that's okay. How we can verify or determine if it's going to be a solution is just take the point and substitute it into the equation. So if we take that first equation, 3 times the x value would be 3 plus 2. If we do 3 times 3, that is 9, plus 2, this equals 11. And so this checks out for our first problem. Now if I do the second equation, negative 5 times 3 plus 2. Negative 5 times 3 is negative 15, plus 2 is negative 13, and this checks out. So 3, 2, this coordinate pair is a solution. And we could also check this using the graphing calculator. So you could type in the computation that I have written out here. If you can't do that in your head, that's okay. You can type this into the calculator and see that this would be equal. And so we would have a solution here. In B, see if you can pause for B and see if the point 1/2 negative 1/3 is going to be a solution. Okay, so hopefully you figured out that this is not actually a solution. So if we check this again, we want to substitute. So the x value is 1/2. The y value is negative 1/3. And if you could do this in your head, that's great. I'll actually go ahead and show you this out on the calculator. So for this one, so 4 times 1/2 plus 15 times negative 1/3. This is going to equal negative 3, and so this equation actually does not equal. Now we could go ahead and type into the second one and see that it does not equal for the second equation as well, but all we need is 1. For it to be a solution, the point has to make both of these two equations equal. And so here in the first one, if we substitute it in, what that would say is negative 3 is equal to 7, and we know that that is not true. So 1/2 negative 1/3 is not a solution. So what we're looking for here when we find solutions to systems of equations, they can be written as points, that's okay, or they could be written as an x value and a y value. What we're looking for is an x and y value that makes both of the two equations equal. Now, there's three methods that we're going to use to find these solutions. The first one is graphically. So basically, we're going to graph the functions. Now, what we want to do to graph the functions, we're going to look at how to do this on the graphing calculator. If you have Desmos, you can do this on Desmos, and it works out pretty nicely. But you can also do it on the graphing calculator. It takes a little bit more work, but we'll go through the steps in the graphing calculator because that's going to be something that's available to you too at all times. So let's go ahead and take a look at 2a. If I want to solve this graphically, again, we said we were looking for the intersection points. In order to type it into my graphing calculator, I need y by itself. And so what I want to do here for this first equation is get y by itself. So that first equation, what I might do here is subtract 4x from both sides. So if I subtract 4x here and subtract 4x there, it's going to give me negative 3y equals 9 minus 4x. Or if you put negative 4x plus 9, that's okay as well. Then I would divide by a negative 3 and simplify where we can. So the first equation is y equals negative 3 plus 4 over 3x. And I can go ahead and type that into my calculator. Negative 3 plus 4 divided by 3x. Now I can do the same thing then for the second equation. So here I might add 2x to both sides first. So y equals negative 5 plus 2x, or 2x minus 5. And then go back to my graphing calculator and go ahead and retype that, or type that one in down at a separate line. So 2x minus 5 or negative 5 plus 2x, doesn't matter. Now I'm going to hit the zoom and I'm going to hit the 6 button here just to make sure my window is on the standard window. And I can see where they cross. So what we need to find is the intersection key. Excuse me. Remember on your graphing calculator, the intersection key is by hitting second and then go into the calculate menu, which is trace. And you can go down and select intersect. It'll say first curve, so just make sure you're on one of the lines, hit enter. It'll say second curve, make sure it's on the second line, hit enter. It'll ask you to guess, you don't need to worry about guessing, and there's our answers. X equals 3 and y equals 1 would be the solution to this system of equations. Now if you wrote that as 3, 1, that would also be okay. So again, what we want to do here is we want to get y by itself, then graph and find the intersection point. Let's go ahead and take a look at another example. Let's do b together. So in the numerator, or sorry, not the numerator, but in the equation listed first, here I might subtract 3x from both sides. That gets y by itself, so y equals 2 minus 3x. So I'm going to put that into my calculator. I'm going to clear out the ones that I had in there previously. So 2 minus 3x. Then in the the second equation, I want to get y by itself again here, so subtract 5x. So that gives me 3y equals 12 minus 5x. Now I need to get rid of the 3 in front of the y, so I divide by 3. Simplifying where I can, y equals 4 minus 5/3 x. So go ahead and type that in and graph these. And there I can see an intersection, so hit second, trace, to get me to the intersect, or the calculate menu, go down and select intersect. Where the first curve, you're on one of the lines, hit enter. It says second curve, you're on the other line, hit enter. And then when it guesses, you don't need to worry about guessing again, just hit enter. And so there's our solution. X equals negative 1.5, y equals 6.5. So there's a little work that we have to do here when we solve them graphically, because we have to get y equal to, or both equations set equal to y by itself. And then we can type the equations into the calculator and let the calculator do the harder computations for us. See if you can do the third one here. See if you can do C. So I'm going to go ahead and pause the video, come up with an answer for C, and then we will play and check the video. Okay, hopefully you had enough time there to get an answer. So let's go ahead and solve now for Y. So Here on this top equation, if I want to get y by itself, I would subtract 3x. So 2y equals 12 minus 3x. Then divide by 2. So y equals, sorry, divide everything by 2 here. Show that step. So y equals 6 minus 3 has x. So I do want to go ahead and type that into the calculator. Again, if you wrote this as negative 3 halves x plus 6, if you wrote it in the format of y equals mx plus b, that's okay. If you're graphing it by hand, we might want to write it in that format, but our calculator does this format as well. On the second equation, I would subtract by x, so negative y equals 9 minus x, and then here I do need to make sure that y is positive, so I need to divide by negative 1. So y equals 9, sorry, negative 9 plus x, or y equals x minus 9. As I graph those, I do see that intersection point. So second, trace, choose the fifth option. Enter on the first curve, on the second curve, and no need to guess. X is 6, y is negative 3. And there we have our solution. Okay, so graphically, it's not a lot of work. Rewrite the equation, set it equal to y, substitute that into the calculator, and then find that intersection point on the calculator. Now, there are some algebraic methods that we're going to use as well. The first one is substitution. So if you're a person who likes laid out steps for you, I have the 4 steps, and we're going to go through these 4 steps. You may want to take a moment to pause the video and record those 4 steps. We're going to go through them one by one in each of the 3 problems. The first problem, 3a. So in order to use substitution, we want to rewrite one of the equations for a given variable. Essentially, we want to get one of the variables by itself. Well, 3a, this is nice. Step number 1 is already done for us. The y is already by itself. So now we can go to step number 2, which is substitute that expression into the other equation. So what I want to do here is I want to take what y is equal, this expression x plus 2, and substitute it into y for the first equation. So remember, substituting is just replacing one variable or expression with another. So if I take that first equation and rewrite it, it would be 4x plus y, but now I'm getting rid of the y and substituting in x plus 2. And then it's equal to 4. This is an equation that I can solve. It's got one variable, so we can combine the two x's. 4x plus 5x, or sorry, 4x plus x is 5x. And now I can go ahead and solve for x. Subtract by 2, so 5x equals 2. And then divide by 5. So x equals 5 halves, or if you wrote this down as, sorry, I wrote it as 2 over 5. Let's try that again. X equals 2 over 5, not 5 halves. So if you wrote this down as 0.4, that would be okay as well. Now that's the solution for x, but we want to figure out the solution for y. So now what we can do is we can take this x, the step number 4, and substitute it back into either of these two equations to solve for y. I'm going to use the second equation because this is where y is by itself. So I'm going to take y equals x and replace x now with 2/5 plus 2. So 2 is just 10/5, so y equals 12/5. If you wrote this as 2.4, that would be okay as well. So the substitution method is done by getting one variable by itself, then substituting that into the other equation, solving for a variable, and then repeating the process until you solve for both. Let's take a look at B. In B, it's not quite as easy because neither of these have a variable by itself. So let me go ahead and use the bottom equation here to get y by itself, because this isn't too hard. Well, what I would do here first to get y by itself is to move the 8x to the other side. So subtract 8x from both sides. So this would give me negative y equals 6 minus 8x. Then I would want to divide by negative 1, so y equals negative 6 plus 8x. Now again, once we get y by itself, we want to go back to the other equation and substitute it in. So I want to go ahead and replace this y right here with negative 6 plus 8x. So I'm going to take that first equation and rewrite it. 2x plus 5 times. Now remember, this is going to be multiplied by 5, so I need this in as a quantity, because because I need to remember to distribute here when I simplify. So as I simplify, 2x minus 30 plus 40x equals 5. Combine my like terms, so 40x plus 2x is 42x minus 30 equals 5. Add 30 to both sides. 42x equals 35. Then finally, divide by 42. So x equals 35 over 42, which simplifies into 5/6. Now, real quick, if we do this in the calculator, if I do 35 divided by 42, I'm going to get a repeating decimal. So what I want to do is change that into a fraction. You can do that by hitting the math key and then enter for fraction. And there we have the exact answer. So we don't want to round this answer if we don't have to, and we don't have to here. Now, if I want to figure out y, I can take this x and put it back into that equation. So y equals negative 6 plus 8 times 5/6. And we can do that in the calculator. So negative 6 plus 8 times 5/6 gives me another decimal. I can turn that into a fraction. So y equals 2/3. So using the substitution method, getting y by itself, substituting that in, solving for x, and substituting that in to solve for y, I have my solution here. X is 5/6, y is 2/3. Again, if you want to write that as a coordinate pair for your solution, that's okay. Go ahead and see if you can pause the video and do C. So solve C using the substitution method. Hopefully you got an answer there for C. If you got x equals 4 and y equals negative 3, then you did this correctly. So let's go ahead and let's see how we got there. So what I would do here is I would use the bottom equation to get y by itself, because that's a simple step, one step. Y equals 17 minus 5x. Now I can take that 17 minus 5x and substitute that back into the first equation. So this would be 3x minus 4 times 17 minus 5x equals 24. So then I can distribute the negative 4. So negative 4 times 17 is negative 68. Negative 4 times negative 5x is positive 20. X, combine my like terms here, so sorry. 3x plus 20x is 23x minus 68 equal to 24. And I would add 68 to both sides of the equation, so 23x equals 92. Divide by 23 and find out that x is 4. So there's part of my solution. Now I can go back to any of these equations and substitute in the 4 for x to solve for y. I'm going to choose this equation right here because y is already by itself. And so if I want to substitute in the 4 to solve for y equals 17 minus 5 times 4, which you could type into your calculator and come up with negative 3. Now, one of the things we can do here is we can also check these answers to see if they're correct. You could graph the equations and see if they come up with the same intersection. Or you could do what we did in problem number 1. I could go back and I could put in my x values. So 3 times 4 and my y values, negative 4 times negative 3, and see if the equations are equal. It equals 24, so that's good for the first equation. So let me do 4 times the x, 5 times the x, which is 4, plus the y, which is negative 3. That equals 17. It's good for the second equation. We know we have an answer there. So this first method is substitution. We primarily use substitution when it's pretty quick and easy for us to get one of the variables by itself, in this case y. Now if it's not, another method that we have is what we call elimination. Elimination is another way that we want to get down to a single variable that we can solve and then put that answer back in to come up with the other variable. So if you need to write down the steps, there they are. We'll go through the steps one by one. So first, it says write each equation in the same form. So notice that in 4a, these are similar looking equations, but they're not in the same order. We want them to be in the same order. So I'm going to rewrite the second equation to match the first. 2x minus 3y equals 7. then 5x plus 6y equals 4. So just reordering the terms. Now, the second says multiply one or both equations by a constant, just a number, to create opposite coefficients for a variable. So what I want is I want in front of the x or the y, I want one of those to have a positive number and the other to have a negative number of that version between the two different equations. So if I look here, I'm going to look at the y's. So this is a negative 3y and this is a positive 6y. How could I make one of those numbers those numbers the same with one being positive and one being negative? If you said multiply the second equation by 2, then you'd be correct. Now, I can't just multiply the y by 2. I need to multiply the entire equation by 2. So what that gives me now is 2 times 2x is 4x, minus 3 times 2 is 6y. Sorry, minus 3y times 2 is 6y, and then 7 times 2 is 14. Now, the second equation I did not change, so I'm going to leave it the way that it was written. So now I can see that these two variables, y, have opposite coefficients. So in problem step 3, it says combine the two equations and solve for the remaining value. So basically, I can add the two equations. So I can take 4x plus 5x, which is 9x, negative 6y plus 6y, which is 0, so those essentially subtract out. 14 times 4, or sorry, 14 plus 4, which is 18. And now this gives me a single variable equation that I can solve for x. Finally, I want to go back to one of these two equations and use it to solve for y. So what I can do, it doesn't matter which one I use. I can take the 2 and put it back into either equation for x, and I'll solve to get y by itself. So what this would look like, this bottom equation, 6y plus 5 times 2, which is 10, equal to 4. So I would subtract the 10 from both sides. Again, 5 times 2 is just 10, so I'm subtracting 2 from both sides, or 10 from both sides. Then dividing by 6, y equals negative 1. So here we multiply the equations by sometimes both equations by the same number, sometimes an equation by or both equations by a different number to get some of those variables to cancel out when we add the equations together. Let's take a look at B. The first step, again, is to rewrite these in the same format. So notice that the y and the x in the bottom equation are on the same side. I'm going to go ahead and rewrite it to look the same here. So I'm going to add the 3y over, so plus 3y here essentially. So this is more than just reordering, but it's still an equivalent expression. 2x plus 3y equals 17. 4x minus 5y equals 12 because I did not mess with that equation. Now in this case, what I could look at is, yes, the 3 and the 5 have opposite signs, but it's not an easy multiplication necessarily to get them to be the same number. The x's is an easy multiplication. What can I get the 2 to multiply to 2 to turn it into 4? If you said 2, you'd be correct. But we don't just want a positive 4. We want a negative 4 because we want those to cancel out. So I'm going to multiply this first equation by negative 2x. So that's going to give me negative 4x, sorry, negative 2. So negative 2 times 2x is negative 4x. Negative 2 times 6 is, sorry, negative 2 times 3y is negative 6y. Negative 2 times 17 is negative 34. I did not change that second equation, so I'm just going to continue to rewrite it. Now, we can add these. And when we add these, what happens to the x's? If you said they cancel out, you'd be correct. So that gives me negative 11y equal to negative 22. So I'm adding the common terms, and that simplifies that expression so that now I can divide by negative 11 and come up with y equals 2. Now it's a substitution back into one of the equations to figure out x. So I'm going to use the 2x equation equals negative 3 times 2 plus 17. You could take negative 3 times 2 plus 17 in your calculator to figure out negative 3 times 2 is negative 6 plus 17 would be negative 11. Sorry, positive 11. And then divide by 2. So x equals 11 over 2. And similar to the last set of equations, I could throw these numbers back in there to check to see if they would work out. And we'd find that these would be good. Now let's take a look at C. Well, the last question I had you do the third problem by yourself. If you want to stop the video here and do the third problem by yourself, you can, but let's go ahead and do C together because C is a little bit more complicated. What we have here is fractions. So what I would do personally, because most of you guys don't really like fractions, is I would get rid of the fractions. So what can we multiply that would get rid of a 1/6 and a 1/4? Basically, what's the least common multiple of the denominators? If you said 12, you'd be correct. So both 6 and 4, you can multiply 6 to get to 12. You can multiply 4 to get to 12. So I'm going to multiply the top by 12 to get rid of the fractions. So negative 1/6 times 12 would be negative 2u. 1/4 times 12 would be 3v. And 4 times 12 is 48. Now, I'm going to do the same thing on the denominator. I'm going to get rid of the fraction before I worry about eliminating. So I'm going to multiply by 6 here. So to get rid of a 2 and a 3, I can multiply by 6. So that would give me 3u minus 4v equal to negative 66. So here we have gotten rid of the fractions, which is probably the hardest part for most people. Now I need to do the elimination method, because if I were to try to add now, I'd still end up with two variables, and so none of the variables would cancel. If I look at these, there's no quick, easy multiplication to get rid of the coefficients if I just multiply one of the equations. I could use a fraction, but instead, let's multiply both of the two equations. Let's take a look at this negative 2 and this 3. One's negative, one's positive. That's good. What number can I get them both to multiply to? If you said 6, that would be correct. So let's multiply the first equation by 3 and the second equation by 2. So if I do that, if I multiply the first equation by 3, that's going to give me, sorry, let me get rid of this line here. Multiply the first equation by 3, that's going to give me negative 6u plus 9v equal to 144. Again, you can multiply those numbers in your calculator. I'm going to multiply the bottom equation by 2, so that's going to give me 6u minus 8v equal to negative 132. So multiplying everything in the top equation by 3, everything in the bottom equation by 2. Now, what that does is it allows us to eliminate the v's, or the u's. So in this case, it wasn't just like A and B where I multiplied just the top. I multiplied both of these by different numbers so that I could now cancel out the u's. And when I do that, it actually takes the v down to a single number, which is nice. Now there's no more work. V is 12. No more work for that specific equation. Now I do want to be able to figure out what u is, so I can take one of these equations and now substitute in for v. So let's take this first one, so negative 1/6 u plus 1/4 times 12 equals 4. 1/4 times 12 is 3, so negative 1/6 u plus 3 equals 4. Subtract 3 from both sides, so negative 1/6 u equals 1. Multiply by negative 6, so u equals negative 6. There we have it. So fraction equations people often get a little bit confused on. The elimination method is nice with fraction equations because you can use a number to multiply to those equations to get rid of the fractions. Then we can work on the eliminating and then solving for variables. Okay, so those are the 4 steps that we're going to follow using the elimination method. These are our 3 basic algebraic or 3 methods that we're going to use to solve system of equations. Graphically, substitution, and elimination. Now, there are some things that come up, some inconsistencies or some issues that come up when we start graphing or solving systems of equations. Every equation that we've looked up so far has been what we call an independent equation. So let's take a look at it from a graphical perspective. All of these were linear equations. So here's a linear equation, and here's a linear equation. This could be an example of something we just solved. These two linear equations intersect in exactly one spot. their slopes are different. If we looked at the lines, those two slopes are different. Doesn't matter what their y-intercepts are, but their slopes are different. When this is the case, it's going to have one real solution. And that's what we've looked at for all of our answers so far. Now, there are some cases that graphically may look a little bit different. So what if we had this equation that looked like this, and then we had a secondary equation, and we could have a secondary equation that looked like this. Basically, they overlapped. So in this case, if we're talking about a line, again, remember the line format is y equals mx plus b. The slope from the first line is the same as the slope from the second line, and the y-intercept from the first line is the same as the second line. In this case, all of the numbers overlap here, so this would be all real solutions. So whatever the line is would be a solution. Any point on that line is going to be a solution to that system of equations. So it has an infinite number of solutions. We could also have what we call inconsistent equations. And so let's say we have these two lines. It's not perfect, but you can get the idea here that these two lines are parallel. So their slopes are equal, but their y-intercepts are not equal. So what do we know about two parallel lines if they don't have the same intercept? They never intersect. So this does not have any real solutions. So most of our equations will be independent. We'll come up with one real solution. But sometimes they'll be dependent, or sometimes they'll be inconsistent. And so let's take a look at what happens algebraically to show us those three different instances. So problem number 5 tells us to solve the systems using an algebraic method of a choice and determine the system if the system is independent, dependent, or inconsistent. So let's go ahead and take a look at 5a. Go ahead and see if you can solve for x and y in 5a. Go ahead and pause the video and solve now. Okay, hopefully you got a solution. What I'm going to use is substitution here. I'm going to use substitution because y is already by itself. Could use elimination. Elimination wouldn't be too difficult here, but this one's pretty quick if it's substitution. Negative 10x plus 35, I'm going to substitute the y. I'm going to replace it with 0.25x. And that equals negative 5. So as I simplify here, negative 10x plus 8.75x. So distributing the 35 into the 0.25 equals negative 5. Combine the like terms, so negative 1.25x equals negative 5. Divide by negative 1.25. And finally, we have that x equals 4. So here's part of our solution. And then we can take 4 back into y and substitute. And then y equals 1. So there's the other part of our solution. This would be independent. This is what we've been working on up to this point, where we come up with one answer. One value for x, one value for y. Now let's take a look at b. I'm going to solve b using substitution as well, because this one is not much more difficult here. The only thing I need to do in this first equation to substitute is divide by negative 1. So that would give me negative 6x plus 22 equals y. So if I'm going to substitute, I'm going to take this expression for y and put it into the second equation. So 3x plus 1/2 times, remember we want to put that negative 6x plus 22 in parentheses, equals 11. Distribute the 1/2, so 3x minus 3x plus 11 equals 11. 3x minus 3x is 0, so this simplifies to just 11 equals 11. So this is something that's true. It's a true statement, but it doesn't tell us anything about x and y. Well, when you get into a solution process and you go through the steps algebraically and it's done correctly and you get a true statement, this means that all real solutions would be true. So we didn't actually have to find what x and y were, but they're going to be all real numbers. This would match up with the second option. This would be a dependent example algebraically. So when you come up with all real solutions, this is dependent. Another way that we could look at this is if we simplify this to rewrite for y, we would notice that they would have the same slope and the same y-intercept. Now let's go ahead and take a look at C. Solving this one algebraically, this one's not the best, but I'm going to go with substitution again. So let's go ahead and divide by 0.5 here to get y by itself. So if I divide the second equation by 0.5, that's going to give me y equals negative 1.5 divided by 0.5. You could do that in your calculator. That would be negative 3. 2 divided by 0.5, that would be 4. And now I can take this equation and substitute it back into the first one. So substitution in all three of these cases is probably quicker. If you did it during using elimination, that's okay as well. So I get 1.2x plus 0.4 times negative 3x plus 4 equals 5. Again, we need to distribute, so 1.2x plus negative 1.2x plus 1.6 equals 5. What happens to the negative 1.2x and the 1.2x? They add to give you 0. So 1.6 equals 5. This is not accurate. It's actually not true. So here we come up with a false statement. This means that there are no real solutions. So for this problem, this would actually be inconsistent. Sorry, I think I spelled inconsistent incorrectly there. Let me fix that spelling. There we go. So this would be what we consider inconsistent because it does not have any real solutions. If we were to rewrite the equations, we would see that the slope is the same and the y-intercept is the same. So algebraically, if you're going through the process of solving, if you get one value for x and one value for y that works, that's independent. That's your only solution. If you get a statement that is just true, it tells you nothing about x and y, that's going to be all real solutions. That is dependent. If you get a statement that is false, that tells us that there are no real solutions. This is an inconsistent solution system for the system of equations. Now, that brings us to our last section in the SE.1 notes. Systems and modeling. So basically what we can do is we can take systems of equations into a word problems. So what I did with the first couple ones is I broke them down into steps, and then on the last one we're going to put all the steps together at one time. So problem 6a, problem 6 gives us a scenario. A jeweler is commissioned to create a piece of artwork that will weigh 14 ounces and consist of 75% gold. She has on hand two alloys that are 60% and 40% gold, respectively. How much of each should she use? So it says using X for the amount of 60% gold alloy and Y for 80%. Write a linear equation to represent the weight of the artwork. Well, what we know about the weight of the artwork, if I go back to the original problem, is at the end it has to be 14 ounces. So whatever she uses of 60% X and whatever she uses of 80% Y, that has to equal 14. It says using the same variables, write an equation to represent the percentage of gold in the artwork. Well, this is a little bit more complicated. What we have to take into account here is both weight and percent. So at the end, this should be 14 ounces, and it should be 75% gold. So at the end, 14 ounces times 0.75. Remember, we have to convert percents to a decimal. This is the weight of just gold at the end. So 14 times 0.75. There would have to be 10.5 total ounces of pure gold at the end. Now, how do we get there? And we'll come back to this 10.5 number. We'll simplify in a second. Well, how we get there is we take this 60%, which is X. So however much X weighs times 0.6 for 60%, plus however much Y weighs times 0.8 for 80% has to equal this 14 times 70%. So if we simplify this, 0.6x plus 0.8y equals 10.5. So it says use a graphing utility to locate the solution for the system of equations written in parts A and B. So remember, in order to graph this, we need y by itself. So in the first equation here at the top, it's probably a quick fix to get y by itself in part A. Subtract x, subtract x. So y equals 14 minus x. I can graph this in my graphing calculator. Then for the other one, it takes a little bit more work. Subtract 0.6x, so 0.8y equals 10.5 minus 0.6x, but then I do need to divide by 0.8. So I'm going to come back to this graphing portion in just a second. Let me clear that out. I'm going to come back to this. So y would be by itself. 10.5 divided by 0.8 is 13.125. We're not going to round that. Let's just use that whole decimal. 0.6 divided by 0.8 is 0.75x. So y equals 13.125 minus 0.75x. Now, if I go take a look at the graph on this, it's going to take a second, but I can't really see the intersection point. So what I want to do is I actually want to make this a little bit. We see it's going to be somewhere over here, but it's not quite tall enough. So I'm going to click the window key, and I'm going to zoom out a little bit. Or you can hit the zoom key, and you can hit 3, and you can zoom out that way. And so now I see the intersection a little bit better. Make sure that's on the screen. So hit second, trace, go down to intersect, make sure it's on the first line, then the second line, and then hit enter along to guess. Oops. This stuff should be over here. So I graph those two equations. I find their intersection point on the graphing calculator, and now I have my solution. So x equals, let me get back over here, x equals 3.5 and y equals 10.5. So those are my two solutions graphically. Finally, D says present your answer found in part C with the context of the problem. So after we find the algebraic solution, we want to make sure we go back and we describe what it is that we're finding. So remember, X was the amount of 60% gold alloy. So the amount in this problem specifically was in ounces. If we go back and we read the original equation, it said in ounces, the original problem. So there are 3.5 ounces of 60% gold alloy that she must use. Y is 10.5. What does Y stand for? Y stands for the 80%. So there's 10.5 ounces of 80% gold alloy. And we could go back and we could check this again. We could go back to our original equation here and put in X that's 3.5 and 10.5, and we'd see that it's 14. We could go back and put it in this equation and see that that would equal 10.5. So in order to make a piece of artwork that weighs 14 ounces and is 75% gold, she has to use 3.5% or 3.5 ounces of the 60% alloy and 10.5 ounces of the 80% alloy. Let's take a look at another problem where it's broken down like that. Problem 7 says, Karen's at-home business makes large decorative candles for all occasions. Her costs include materials at $3.50 per candle and rent and utilities that average $900 per month. If her candles sell for $9.50, how many candles must be sold each month to break even? So it says, write a linear equation, C of x, to represent cost, C, in terms of x candles made. So in here, there's a couple things that come into cost. Her costs are $3.50 per candle. So we don't know how many candles are made, so we're using this as x. 3.5 times x. But that's not the only part for cost. Notice that utilities average, or rent and utilities average $900 per month. So her cost is an additional $900. So let's write an equation R of x to represent the revenue R generated by x candles made. So revenue is the money that's brought in. Remember, revenue is found by taking the number of candles, which is X, multiplied by what they sell for, which is 9.5. So 9.5x. There's no other way that she makes money, and so this would be the only part that we would be looking for. Now, this is our system of equations. Now, remember that C of x and R of x basically just stand for y. So we can basically look at this as just a y, and this is just a y. So in this equation, we don't have to do any work to graphically rewrite these. So what we can do is we can just go to our graphing calculator and type in these two equations. So let me clear out what's in there previously. 3.5x plus 900 and 9.5x. Let me clear out everything else. Sorry, let's put that in 9.5x. Now, let me go back to the standard window. Assuming you were here in the standard window, if I hit this graph, I only see one line here. So this is actually not going to work out for me. So what I need to do is I need to increase this window. Again, we can hit the zoom key and we can zoom out if we want. Really what we are primarily focused on is just increasing the x's. So if you hit the window key, currently our x is about candles. So I'm going to change my x minimum to 0. I'm going to change my x maximum to, I don't know, let's say 250. Then I'm going to hit zoom and go down to 0. Zoom fit. What this is going to do is going to adjust the window to better fit my graph based on what I wanted from 0 to 250. So now this gives me a 0 to 250 on the x-axis, and it fits it on the y-axis, and I can see the intersection. So second, trace, intersect, hit enter on the first curve, the second curve, and no need to guess. And there we have the intersection point. So x equals 150, y equals 1425. So it says present your answers found in part C with the context of the problem. Well, on the last problem, we were looking for two answers, basically. We were looking how much of each alloy do we need. In this problem, the only thing we were looking for is how many candles do we need to sell. I'm not worried about what the cost or what the revenue is. We do get that number through the Y, but really all we need to know is 150 candles need to be sold. And there we have our answer here for part D. So breaking these down into writing equations and then solving them graphically helps us to then put context to our answers to answer the problem. For all of our word problems, we are going to be able to solve them graphically. The only time you have to solve algebraically is if you're directed to. So let's go ahead and take a look at problem number 8, our final problem here in the notes. It says an airplane flying due south from St. Louis to Baton Rouge, Louisiana, has a steady tailwind to help complete the trip in only 2.5 hours. On the return trip, the same wind slows the flight and it takes 3 hours to get back. If the flight distance between these cities is 912 kilometers, what is the cruising speed of the airplane and how fast is the wind blowing? So there's two things that we're looking for here. Now, this didn't tell us what to assign variables to, so let's make our own variables. One of the things that we're looking for is the speed of the airplane. So I'm going to let that be A because it tells us nothing about the kilometers in this case, kilometers per hour, how fast the airplane is moving. The other thing that we want to find is the speed of the wind. Again, it tells us nothing about the rate of the wind, so I'm going to make that a W. Now, one thing to remember that you have covered before in previous classes is that distance, you find distance by taking your rate or your speed times time. That's how we find distance. So this is how we're going to set up our equations. The first equation is the trip from St. Louis to Louisiana. The distance is 912 kilometers. So 912 equals the rate is the speed that it's traveling. Now, it doesn't tell us how fast the plane is going, but what it tells us is the tailwind is helping complete the trip. So the rate is going to be how fast the airplane moves plus how much the wind is pushing it. The time on that trip is 2.5 hours. So we take distance equals rate times time to come up with this equation. 912 the distance, the rate is A plus W because the wind is helping, times the time, 2.5. Now we need another equation for on the way back. On the way back, the wind slows. So the distance is still the same, going the same amount. But this time the wind is taking away from the airplane. It's slowing it. So A minus W, and then it takes 3 hours. So these are our two separate equations. Now, let's go ahead and distribute here to rewrite these a little bit. So 912, if I distribute 912 equals 2.5A plus 2.5W, and 912 equals 3A plus 3W. So let's actually graph this. So in order to graph this, we need to get either A or W by itself. So let's take the first equation and let's get, let's say A by itself. Let's use A as, or yeah, let's just use A as our variable we're going to get by itself. So what I would do here is I'd subtract 2.5W from both sides. So I'm going to write this over here. 912 minus 2.5W equals 2.5A. Now I need to divide by 2.5 to get A by itself. So in the calculator, let me clear out of this, clear out of that. 912 divided by 2.5 equals 364.8, and then negative 2.5 divided by 2.5, so that would be 1, so minus, or negative 1, so minus 1W would just be minus W equals A. So I can put this equation into my calculator. Let's use A as W. I probably should have done that from the start, but let's just use A as W. I'll go back here and add this in. And, sorry, let's use A as Y because that's by itself, and X is W. So Y is by itself, so 364.8 minus X. In your calculator, you have to use X and Y. So I probably should have used X and Y, but that's okay. Now, let's do the other equation, the same method. Let's take the 912 and let's get A again by itself. So subtract 3W. So 912 minus 3W equals 3A. Divide by 3. So 912 divided by 3. If you need to do it in your calculator, it's okay. 304. I'm not even going to divide 3 by 3 because everybody should know that's 1. Did it on the last one, but I'm not going to do it again. There we go. 304 minus W. So again, we're treating W as X on the calculator. So if I graph this under my normal circumstances on my calculator, I see nothing. So I need to extend my window. So I'm going to take my Y minimum to 0, or my X minimum to 0. I'm going to take my sorry, let's leave the Y's alone. Let's take X minimum to 0, which is the rate of the wind. And I don't know how fast the wind blows. Let's make it to 100. Tornado speed. And hit zoom, 0 to fit the graph. We don't have any intersections there. Ooh. Hold on just a second. I think I've made a mistake. Haha, I see my mistake. And hopefully you guys were able to catch this. What I did here, this, when I distributed this 3 to the W, that should have been a negative W here. So this changes things a little bit. This should be a negative W there. So I should be adding 3W here. So that would make this positive and would make this positive. There we go. That makes a bit of a difference. So let's make this 304 plus X. And there we should have the correct graph. Sorry for that mistake. If I knew how to edit it out, I would, but we're going to have to roll with just going back and fixing it. So be careful when you distribute what your signs are. This should have been a negative 3W, making this plus W. So now as I take a look at the graph, I can find second trace. I can find that intersection. enter on the first curve, enter on the second curve, and there's my intersection. So what this gives me is x, which we said was w, is 30.4, and y, which we said was a, is 334.4. So let's go back to the context of the problem. So the rate of the airplane, and we do want to make sure we include units here, is 334.4 kilometers per hour. And the rate of the wind, or how fast the wind is blowing, is 30.4 kilometers per hour. And there we have it. So, solving systems of equations. Two linear equations, or linear equations given two variables. We can use three different methods: graphing, elimination, and substitution. Each have their own purpose and their own kind of shortcuts. Graphing is definitely probably a little bit shorter of work in most cases, and we will graph when we can using word problems. The algebraic methods, substitution and elimination, will be used when we are told to in those certain situations. But you can use all three. If you do it correctly, all three of them should get you the exact same answer in each situation. At this point in time, you guys should be finished with the notes. Make sure you have good notes taken down, because you guys can use that when it comes around time for the quiz. You should be working on your homework, which is going to be found in IXL. Again, to complete, considered complete on the homework, you have to have a SMART score of 80 plus on each section, or a SMART score of 40 plus with at least 15 minutes of practice on each section. Pay attention to Google Classroom for the next Zoom session, where we will be able to go over questions that you have on the notes or questions that you have on the homework in preparation for our assessment. Thank you guys for tuning in, and have a great day.